Yeah, he called it Live Force or Vis Viva, and this was this is the beginning of the modern industrial age because it found a direct application. The idea that the work that can be done depends on the velocity of something that's expanding, or like steam, or explosion, gunpowder. And in other words, all the machines that they had, the lever, the pulley, the windlass, and so on, these were all static machines. But he was the one who understood the importance of dynamics. He created the science of dynamics, and it grew out of lengthy studies that he did in a number of areas. So you'll see that his thinking was very multiply connected. He was looking into the nature of the infinite, what causes cohesion, and what causes matter to stay together in a solid, or relatively speaking, in a liquid. And he was looking at the relationship of mind to matter. So he was showing, and then he was also interested in this. He had two labyrinths. One was called the labyrinth of the continuum, and the other was the labyrinth of free will versus determinism, or the paradox of God's wisdom and power, and the fact that there is so much evil in the world. So he was working on all these things at once, and I think that's not to lose sight of that, because each thing fed in to the other and allowed him to end up with a whole system of thought, which nobody has had a system of thought since Leibniz except Lin. So you get more appreciation now. In terms of the technology, I mean, he was part of a kind of a science driver project with Colbert was the minister under Louis XIV, and he assembled in the I guess it was late 1660s, early 1670s. He assembled a team under a Dutch scientist, Huygens, and Leibniz was one of them. He was just 1672. He was 26 years old, and another fellow there in the team was a guy named Dennis Papin, Papin. He was a medical doctor, and and then and they were working on, basically they were working on both basic science. Leibniz was working on the calculus as part of the project, and that's where he developed the calculus. But also they were having a lot of discussions, about the physics of collisions, how to understand what goes on in elastic and inelastic collisions. And Papin, the team was broken up because basically, I mean, there are always particular reasons you'll read about in Leibniz's particular circumstances, but basically it was this contrived conflict with the Catholics and the Protestants. So all these Protestant scientists were basically driven out. So the whole thing was busted up, and then in 1685 they had this thing called the Edict of Nantes. I guess it was anti-Protestant regulations in France. So the thing was busted up. It was all. I don't think we've written anything about this particular situation, but it would seem to be typical of the oligarchy. Anyway, but Papin then he went on to work on use of steam power to, first it was pressure cooker. He developed a pressure cooker, to basically soften up bones so people could eat the bones, and then in around 1690 he started getting involved with trying to develop the steam engine, and with Leibniz. You'll see that Leibniz got into a correspondence with a lot of people about this new idea we'll be reading about the vis viva, and one of the people was Papin, because they knew each other from this project. And so he got, the question was, could you see some of the applications of of explosions was to create vacuums and then utilize the air pressure to do work. So the question with dynamics was, could you create significantly more power than that of a vacuum with steam power? Was there a way to do it? Go beyond the power of the the atmosphere, and so he basically organized Papin around that idea and improving it, and then they went on actually develop a viable steam little vessel go on the water with paddle wheels, and but the thing was sabotaged by the British Royal Society, and so they got control of the invention, and nothing was done for 100 years. You should read Phil Valenti's article. He wrote this in 1979. It's in Fusion magazine. You can, anyone needs it. I have the archive. Jason sent me the archive for those number of years. You could read it. So what would what people have any idea what would you mean by a universal principle? Universal physical principle.
Just gonna take a guess. I was just gonna say creativity.
Louder.
Creativity.
Involves creativity.
Would Lynn's concept of the energy flux density qualify what the way you're defining universal physical principle?
You
Because
say
that's what I think of. Lynn's concept of the energy flux density
Yeah.
as a principle of a metric of actual increase of cognitive power
Okay.
and over nature. I think that's a universal principle.
Uh-huh.
Is that what you mean? Or you
I'm
think
just
it's-
throwing it out. I'm not saying I'm going to give a definitive answer. We'll work on it, but get people's thoughts on it. Yeah.
Well, I think it's a solution solved in a human being's mind that no animal could, to understand, a paradox that sense certainty would give you, one answer or no answer, but the human mind
Mhm.
resolves the paradox.
Uh-huh.
And then with this higher concept that is seen in the mind has the power, which is universally applicable, to other human beings everywhere,
Yeah.
and gives more power over.
So you're saying it's an
nature.
idea which does not involve the senses. It goes beyond the senses.
Yeah, it's
Okay.
it's higher than the senses will give the paradox or
Yeah.
the, what's going on here, but then the mind develops things that are unseen
Mhm.
that only humans could, and that power that is innate
Yeah.
to the human beings
Okay.
gives them power over that,
Power over what?
over the phenomenon that is the
Okay.
footprints appear in
Yeah.
sense certainty.
Okay. Does it have any particular consequences, do you think, of discovery of a universal principle?
Well, yeah, the ultimate test LaRouche is saying is it increases relative potential population density.
Okay, so we actually use it to transform, we actually apply the principle to transform nature.
Yeah.
Yeah, okay, yeah, well, that's Lynn, I think that's Lynn's view. Also, there's a certain intention. The principle expresses an intention in nature, and we then utilize that intention for our intentions. Yeah, I think that's it. That's something Lynn writes about, actually. I don't know if we'll get to it this time, but there's a section in the Noosphere book. He's talking about what are physical principles, and then he talks about the monadology and the idea of intention, and how monads each monad has an intention built into it, has a desire inbuilt in it to do certain things. So anyway, we should just get into the core of this thing. Put up this page 297. A brief demonstration of a notable error of Descartes, and others concerning a natural law. Okay? So, you see, you see it mentions there. You can read that, start reading that. Somebody start reading, you'll see Papin mentioned there. Okay?
The italics?
Just, just read, you start in the beginning.
Read the title, please.
You read the whole thing.
A brief demonstration of a notable error of Descartes and others concerning a natural law, according to which God is said always to conserve the same quantity of motion, a law which they also misuse in mechanics. In this criticism of the Cartesian principle of the conservation of quantity of motion or of momentum, Leibniz began to fulfill his promise to refute the Cartesian physics, and particularly the laws of motion, by means of a new principle. His analysis of the relations of energy expended and work done involves the principle of equivalence as applied to physical processes. Replies were made to the paper by two outstanding Cartesians, the Abbe Catalan in 1686 and Denis Papin in 1691. Both answers involved Leibniz in a series of discussions which led to sharper formulations of his principles. The supplement is a later edition which reflects his thinking at the time of the Specimen Dynamicum. Seeing that velocity and mass compensate for each other in the 5 common machines, a number of mathematicians have estimated the force of motion by the quantity of motion or by the product of the body and its velocity. Or to speak rather in geometrical terms, the forces of two bodies of the same kind set in motion and acting by their mass as well as by their motion are said to be proportional jointly to their bodies or masses and to their velocities. Now, since it is reasonable that the sum of motive force should be conserved in nature and not be diminished, since we never see force lost by one body without being transferred to another, or augmented, a perpetual motion machine can never be successful, because no machine, not even the world as a whole, can increase its force without a new impulse from without. This led Descartes, who held motive force and quantity of motion to be equivalent, to assert that God conserves the same quantity of motion in the world. In order to show what a great difference there is between these two concepts, I begin by assuming, on the other hand, that a body falling from a certain altitude requires the same force which is necessary to lift it back to its original altitude if its direction were to carry it back and if nothing external interfered with it. For example, a pendulum would return to exactly the height from which it falls, except for the air resistance and other similar obstacles which absorb something of its force and which we shall now refrain from considering. I assume also, in the second place, that the same force is necessary to raise the body, A, figure 11, of 1 pound, to the height CD of 4 yards, as is necessary to raise the body, B, of 4 pounds, to the height F of 1 yard. Cartesians, as well as other philosophers, and mathematicians of our times admit both of these assumptions. Hence, it follows that body A, in falling from the height CD, should acquire precisely the same amount of force as the body B falling from the height EF. For in falling from C and reaching D, the body A will have there the force required to rise again to C by the first assumption, That is, it will have the force needed to raise a body of 1 pound, namely itself, to the height of 4 yards. Similarly, the body B, after falling from E to F, will there have the force required to raise again to E by the first assumption. That is, it will have the force sufficient to raise a body of 4 pounds itself, namely to the height of 1 yard. Therefore, by the second assumption, the force of the body A, when it arrives at D, and that of the body B and F are equal.
So is Descartes saying, that the, object would fall from C to D at the same time as E to F?
They'll have the same force.
Same force?
At the bottom.
At the bottom.
According, well, yeah.
What about time?
That we're not discussing.
Oh, okay, all right.
In other words, if it was an elastic or a spring, some kind of elastic holding it, you dropped it, and it bounced back up.
Yeah.
Or a trampoline, I was thinking.
Yeah, something that would bounce, something that would bounce it back up.
It bounced back up. That was essential for his whole thing, because he called it the full cause principle. In other words, the full you want to find things which you can actually compare in a straightforward way. So if the full cause is, if the cause and the effect are equal, then it's going to come back up, okay, to the same height. So that's, and he said they noticed that was true with these pendulums, you know, that Huygens was experimenting with. So that was one of the sources of his ideas, was this collaboration and letters of exchange with Huygens. So it's also more abstractly, it's like the whole is greater or equal to the part, which is something that he applied over and over again. So here's we'll get to here. Now we get to the tricky part. Okay, that's really pretty straightforward.
Now let us see whether the quantities of motion are the same in both cases. Contrary to expectations, there appears a very great difference here. I shall explain it in this way. Galileo has proved that the velocity acquired in the fall CD is twice the velocity acquired in the fall EF. So if we multiply the mass of A, which is 1, by its velocity, which is 2, the product or the quantity of motion is 2. On the other hand, if we multiply the body B, which is 4, by its velocity, which is 1, the product or quantity of motion is 4. Therefore, the quantity of motion of the body A at D is half the quantity of motion of the body B at F, yet their forces are equal, as we have just seen. There is thus a big difference between motive force and quantity of motion, and the one cannot be calculated by the other, as we undertook to show. It seems from this that force is rather to be estimated from the quantity of the effect which it can produce. For example, from the height to which it can elevate a heavy body of a given magnitude and of a given magnitude and kind, but not from the velocity which it can impress upon the body. For not merely a double force, but one greater than this, is necessary to double the given velocity of the same body. We need not wonder that in common machines, the lever, windlass, pulley, wedge, screw, and the like, there exists an equilibrium since the mass of one body is compensated for by the velocity of the other. The nature of the machine here makes the magnitudes of the bodies, assuming that they are of the same kind, reciprocally proportional to their velocities, so that the same quantity of motion is produced on either side. For in this special case, the quantity of the effect, or the height risen or fallen, will be the same on both sides, no matter to which side of the balance the motion is applied. It is therefore merely accidental here that the force can be estimated from the quantity of motion. There are other cases, such as the one given earlier, in which they do not coincide.
Okay. So what do people make of this? Anybody can want to explain what he's saying?
Well, it sounds like force is something different than velocity, or it's almost like the amount of work that you can do, as opposed to, I mean, that's certainly interesting, because he's saying something that falls 4 yards,
Yeah.
weighs 1 pound, is gonna be going faster when it gets to the bottom than something that only falls one yard, even if it weighs 4 pounds more, or if it weighs 4
Well, what would
pounds
this
more.
have to do with Galileo?
That's what Galileo said.
What is he saying that Galileo uniquely observed?
Isn't it that?
I think it was if you drop two objects, no matter of the weight, that they would, they hardly go into the ground together. That's what got
Velocity.
No?
He never talked about time.
In a vacuum.
Well, remember, you're dealing with, it involves the square root, because the velocity acquired is proportional to the square root of the distance fallen.
Right,
So it's not linear,
right.
okay? So in other words, you have the body that falls, a 1 pound body that falls 4 feet has twice the velocity of a body that falls 1 foot, right?
Right.
So if you have, what did he say, you had a 4 pound body that falls 1 foot, and a 1 pound body that falls 4 feet, supposedly they represent the same quantity of motion. But how do the powers compare?
The one that falls farther has greater velocity, twice as much.
The 1 pound body that falls 4 feet has
It's going
twice
as
the
fast.
velocity.
It gets to that
Okay.
point.
So what is how do the quantities of motion compare then in the two?
It seemed to me there was he was making a contrast between force, his measurement of what he called force, and the quantity of motion, trying to prove that they're not equivalent. That,
Okay.
what I heard from this, what I got from it, maybe it's not even, it's just extraneous. I thought he was saying that what he was proving was that the quantity of the motion
Yeah.
is not equal to the force. He could
Uh-huh.
measure the force and the velocity and so forth, but they're not equivalent. He was showing that they're not equivalent.
Uh-huh.
And I don't know what
The
the
force and the
significance
velocity
is.
are not equivalent.
Right, there's one.
Repeat that again?
The force and the velocity were not equivalent.
Yeah, that's what I just said. That's what he's proving. But that's all I heard him prove. That the quantity of the motion isn't equal to the force. And I don't know what the significance of that is. Maybe that's an unimportant observation.
Oh, no.
Is it okay to read that one more time, even though we just had a...
Sorry?
is it enough time to make it in your total, presentation to be kept up with time? I don't know what the schedule is.
Or can you sum it up for us?
Yeah.
I mean, I think we know what it said, but the question is why is force different from the quantity of motion?
Remember what he says, that, he says, so if we multiply the mass of A, which is 1, by its velocity, which is 2, the quantity of motion is 2. On the other hand, if we multiply the body B, which is 4, by its velocity, the quantity of motion is 4. Therefore, the quantity of motion of the body at A, in other words, the 1 pound, is half the quantity of motion of the 4 pound body, yet their forces are equal. Okay? So that's a paradox. Okay? That's the paradox, that they're not, you can't equate, they're not the same. The force is in other words, the work, if you take the force times the, the weight times the distance is lifted, you would think that it lifting 4 pounds 1 foot, or 1 pound 4 feet, they involve the same amount of work. Yet the quantity of motion are not the same, and that's shown by if you drop either of them, and thereby get back the amount of energy work that you did to go up, they are the same. The work done to in other words, the forces are equal, but the quantities of motion are not.
Quantity of motion being the
Sorry?
quantity of motion being the mass times the velocity.
Yeah.
Yeah. are
So
different.
that's a paradox.
To
Okay. So which is right? The question is which of these is right? Okay.
Ernie?
Yeah.
If you put something like gelatin or something, underneath,
Yeah.
and you drop both of these,
Yeah.
could you, what would you see in terms of presumably the amount of work done when they get to the bottom?
That's the thing, 'cause I was wondering which you'd rather have drop on your foot.
Yeah. I mean, we know the velocity is gonna be different.
Yeah.
One is falling for a greater distance.
Yeah.
But how much energy, because the
Force of the
terms get a little confusing, okay, quantity of motion versus force, but what does that really mean?
But see, he's using force in a different way than is in the textbooks today. Force is mass times acceleration. That's how it's defined. But he's talking about work, force times distance. Okay, these are not the same thing. Okay.
Or would you rather be hit by a 1 million ton ball moving at 1 mile per hour, or
A bullet.
a bullet moving at 1 million miles per hour?
Okay.
That's a Reesian choice.
I'm saying, if the 1 ton ball is moving really slow, it's probably not gonna do much to you.
But you can get out of the way.
Yeah.
Unless you're up against the wall.
Or unless it's a very dense ball.
But a bullet will.
All right. Well, shall we continue? With anybody having more questions? Or should we?
You read a number, 1 times 2 is so-and-so. I thought the 1 pound object had to go distance
Goes up 4 feet. Right.
How come when you read, you said 1 times 2, or 1, I maybe misheard
Velocity
you?
is twice.
The difference in velocity.
Velocity is twice.
Oh, velocity is
Going from
twice.
height of 4 down to the bottom, you reach a velocity twice as much as if you drop from the height of 1 to the floor.
So twice the velocity.
This is not simple stuff. Look, nobody thought of this. Nobody thought of what he's done there. Nobody made this connection. Okay, it seems, you know, it's a totally actually a totally extraordinary event in history that he formulated this, and then you see what came out of it was the use of this to you know, for steam power, you know, and other forms of utilizing this factor of the square of the velocity. Okay, it's a non-linear thing that actually is not goes against sense perception, because velocity, you see something moving, so you think motion is real. See, one of the things that he pondered before he came up with this was he finally realized motion is not real. It's all relative. Which body is moving, and which body is moving relative to the other. It was like, you know, Copernicus versus you know people before him, you know, Ptolemy and so on. Is it the sun moving around the Earth, or is the Earth moving around the sun? I mean, which is it's relative question of relative motion, the same thing. And he actually realized this. Descartes did not. Everybody else treated motion as real. In fact, in 1676, he writes a dialogue on motion, and he gets it's all entangled. He's in this labyrinth, you know. He's all entangled in inductive thinking about motion, and with Zeno's paradoxes. And it was only it was just a few weeks later he realized motion isn't real. So there's something else you got to look for. What is it? And also, if two bodies collide, what's real? If the motion between them is not if the motion is not real, there's got to be something more universal involved, something that's not immediately obvious. And so that's part of his thinking. So let's continue.
Where did we stop?
Just read that. You can read that paragraph.
Since nothing is simpler.
Since nothing is simpler than our proof, it is surprising that it did not occur to Descartes or to the Cartesians, who are most learned men. But the former was led astray by too great a faith in his own genius. The latter in the genius of others. For by a vice common to great men, Descartes finally became a little too confident. And I fear that the Cartesians are gradually beginning to imitate many of the Peripatetics, at whom they have laughed. They are forming the habit, that is, of consulting the books of their master, instead of right reason and the nature of things. It must be said, therefore, that forces are proportional, jointly, to bodies of the same specific gravity or solidity, and to the heights which produce their velocity, or from which their velocities can be acquired. More generally, since no velocities may actually be produced, the forces are proportional to the heights which might be produced by these velocities. They are not generally proportional to their own velocities, though this may seem plausible at first view, and has in fact usually been held. Many errors have arisen from this latter view, such as can be found in the mathematico-mechanical works of Honoratius Fabri, Claude Deschales, John Alfonso Borelli, and other men who have otherwise distinguished themselves in these fields. In fact, I believe this error is also the reason why a number of scholars have recently questioned Huygens' law for the center of oscillation of a pendulum, which is completely true. Supplement. It is to be shown that the power required to lift 1 pound 2 feet is the same as the power required to lift 2 pounds 1 foot. This proposition is not only admitted but explicitly applied and regarded as a principle by Descartes in his letters and the short treatise on mechanics which was edited with his letters, and separately as well. It was also accepted by Pascal in his treatise on the equilibrium of fluids, by Samuel Morlet, the Englishman who invented the stentorian tubes, in the hydraulic treatise which he recently published, and by a certain learned Cartesian who has tried to reply to my demonstration against Descartes in the Novellas de la République des Lettres, published in Holland with a number of evasions, though he did not adequately understand my argument. I shall not mention other Cartesians or the opinions of other philosophers, so I can safely apply the principle in refuting the alleged natural law of the Cartesians. The same proposition is confirmed also by the 5 commonly recognized mechanical powers: the lever, windlass, pulley, wedge, and screw. For all these our proposition seems to be true. For the sake of brevity, however, it will suffice to show this in the single case of the lever, or what amounts to the same thing, to deduce it from our rule that the distances and weights of bodies in equilibrium are in reciprocal proportion.
What's the windlass?
That's Archimedes' famous.
No, it's a
You wind it.
You wind it up.
Put my hand behind my back and I'll wind the windlass and I'll move the biggest ship in the world. That's Archimedes.
Pull it. Let us assume AC in figure 12 to be double BC, and the weight B double the weight of A. Then I say A and B are in equilibrium. For if we assume either one to preponderate, B for example, and so to sink to B prime, and A to rise to A prime, and drop perpendiculars A prime E and B prime D from A prime and B prime to AB, it is clear that if D B prime is 1 foot, A prime E will be 2 feet.
You gotta show that. Illustrate.
See, there's an error there, actually.
Oh.
Just go back and I've circled, it's double. You'll see when you see it. It's actually half. You'll see that. If AC is half of
Therefore, that
BC.
Oh,
if 2 pounds descend the distance of 1 foot, 1 pound will ascend to the height of 2 feet.
Let me read that with all people looking at the thing. He says, let us assume AC, figure 12, to be half BC, and the weight B half the weight A. Then I say A and B are in equilibrium. For if we assume either one to preponderate, B for example, and so to sink to B prime, and A to rise to A prime, and drop perpendiculars A prime E and B prime D from A prime and B prime to AB, it is clear that if DB prime is 2 feet, AE prime will be 1 foot.
This is a lever here, is that right?
Yeah.
That's swiveling at sea.
It's like a
What you're
seesaw.
talking, I was,
Therefore, that if 2 pounds descend the distance of 1 foot, 1 pound will ascend to the height of 2 feet. Okay. And thus that since these two are equivalent, nothing is gained and the descent becomes useless, everything remaining in equilibrium as before. It can be shown in the same way that A cannot descend or predominate. So our proposition or hypothesis, so to speak, is confirmed a posteriori, for by assuming it, one can prove that all the common mechanical propositions apply to equilibrium or to the 5 machines. Indeed, I might even risk affirming that there is no mechanical theorem in which our hypothesis is not confirmed or presupposed, or as can be shown, for instance, by the law of the inclined plane, or by fountains, or by the acceleration of falling bodies.
I missed where the square.
Where does the square come in?
Yeah, I missed that.
Well, it doesn't come in here, but it comes when a body is free falling. In other words, the velocity acquired in falling is proportional to the square root of the distance fallen. In other words, if you fall 4 feet, you acquire twice the velocity of if you fall 1 foot. That's where it comes in.
Should we go on?
Right.
Oh, wait, I can't see now. Even if some of these seem reconcilable with that hypothesis, which estimates power by the product of mass by velocity, this is only accidentally, since the two hypotheses coincide in the case of dead forces, tensia mortis, in which only the beginning or end of conatussus, what is that?
Conatus is like an impulse.
Okay, all right, is actualized. But in living forces, or those acting with an actually completed impetus, there arises a difference, just as the example shows, which I have given above in the published paper. The living power is to dead power, or impetus, actual velocity, is to conatus, as a line is to a point, or as a plane is to a line. Just as two circles are not proportional in their diameter, so the living forces of equal bodies are not proportional to their velocities, but to the squares of their velocities. And since we cannot stop with an appeal to authority in this manner, and the mind, which seeks to know, will not be satisfied with mere inductions and hypotheses. We will now give a demonstration of our proposition so that it can be placed for the future among the immutable foundations of the science of mechanics. I assume the single principle that a heavy body falling from any height will have exactly or precisely the power necessary for it to rise back to the same height. If it is understood to have lost no force, sorry,
On its way.
On its way by friction.
you wanna point that, I'm sorry, I don't see it.
No force.
Oh, no force on its way by friction or resistance by the medium or center of the body. Corollary. So a body of 1 pound, which descends on 1 foot, acquires exactly the power of raising a body of 1 pound equal to the first body itself to the height of 1 foot. I postulate, besides, that I am permitted to assume various connections of the heavy bodies with each other and their separation again, and to introduce any other changes which do not involve a change of force. I also make use of threads, axes, levers, and other mechanisms lacking in weight and resistance. Theorem. With these assumptions, I assert that the fall of the body B, figure 13, of 1 pound for the distance B double prime, a height of 2 feet, will have exactly as much force as is necessary to raise the body A of 2 pounds to the height of double A prime of 1 foot. Demonstration. I assume the body, composed of 2 parts, is 1 pound. Now the body B of 1 pound has exactly the power in descending from the height BB prime of 1 foot that is necessary to raise the body E of 1 pound to the height of EE prime of 1 foot by the corollary. If a connection is assumed between them by the postulate, we assume further by the same postulate that the body B in the position B prime is freed from its connection with body E, which remains at E prime, and is connected now with body F.
Can you
Then
move
the
that up a
body-
little, Art, so we can actually see the
Yeah, I'd
whole
like to see
picture?
the body too. Could you?
Maybe you should show the whole,
Yeah,
if
that
you show
would-
people the whole thing. He's showing that it's all linear, okay? You can actually, he's establishing a way you can actually measure what he calls forces by their linear effects in terms of, or the linearity of the effort required to elevate different weights to different distances. They become comparable. And then in turn you compare that with the force of something that is, here there's no question of velocity, although actually people who argued with him said the rate at which you raise it should matter. And he said, no, it doesn't matter. Time does not enter it at all. But you can compare, in other words, you can compare this, the force for lifting things, with the force of things which are in violent motion. In other words, you find a means of comparing that otherwise you wouldn't have. And that's one of the things that he recognized, that you could actually, therefore he reduced these to a common measure. The force involved in raising a body, the force involved with a body that's in motion. You can actually compare the forces in these two cases. It's not obvious you could do that, and he figured that out. He made that. It seems obvious once he tells you, but people didn't things like the calculus and the same thing. I mean, it becomes a lot of what he's saying is obvious once he explains it, but until then no one had thought of it. And this is an interesting question, how he actually
Is this like a pulley?
did this.
Is this a pulley of some kind?
I'm sorry?
Is this a pulley of some kind?
What he's doing.
Yeah, I guess, yeah.
Or
Uh-huh.
windlass,
Yes,
that's what
uh-huh.
He seems to just be comparing the force required to lift a body to the force released.
It
in its
requires
descent.
in falling, yeah. He's
Yeah.
saying they're equal,
Right.
okay? So he's found a means of comparing things. You can compare two bodies which are moving at different speeds because it's a common measure through in other words, you have a linear common measure to work done against gravity.
But it's not actually falling though, is it?
No, that has nothing to do with falling, no.
Right.
No,
because
that's right. There's no velocity involved here at all.
So this is just that you get, it's the same principle as a pendulum, that you get as much out as you put in.
Yeah.
So that it can go back to the same height
Uh-huh.
when it falls.
Yeah.
But that's a different question than this vis viva.
Yes, and people didn't agree. You see, he did not convince a lot of people, especially the Cartesians, you know. But he did not convince a lot of people. So right away, I mean, it became accepted, you know. But the point is that I think that's the point. Yeah. Let's not lose our train of thought. Let's keep going then.
Finish reading that paragraph?
Then
Yeah.
the body B, continuing its descent for the distance B prime, B double prime, would be able to lift the body F of 1 pound for the distance FF prime, a height of 1 foot by the corollary. Therefore, the whole body B of 1 pound descending 2 feet, BB prime prime, has raised the body composed of both E and F or A of 2 pounds through AA prime of 1 foot, but exactly this was to be proved possible.
So the 1 pound object dropping 2 feet raises a 2 pound object 1 foot.
Yeah.
Say that again, Art?
I'm sorry?
1 pound object dropping 2 feet raises a 2 pound object E and F, 1 foot.
Yeah. It's linear, that's the point.
If it was
It
just
doesn't
one
involve a
pound,
square or anything like that.
I'm sorry.
Continue. Somebody wanna continue?
If the matter is carefully considered, it will easily be understood, without any apparatus or figures, that these two things are equivalent. To raise 1 pound to 2 feet, in other words, a pound of 1 foot, and then again a pound a foot, and to raise 2 pounds a foot, in other words, a pound 1 foot, and join to it another pound 1 foot. In general, forces are to be calculated from their effects, not from their time. For time can be varied by external circumstances. Thus, the sphere, C, with a specific impetus, degree of velocity, by whose action it can raise itself to the height of hg on an inclined plane, Lm or Ln, needs more time in proportion to the increasing length of the plane. In either case, however, can't keep an eye on that. It will rise to the same perpendicular height if naturally, as must be done in these problems, the resistance of air and the plane be taken as 0. The force of the sphere will remain the same, whatever may be the inclination of the line in which it lifts itself. I understand here such an effect as itself constitutes a natural force, or one by whose production the impetus is diminished. Such an effect is the ascent or elevation of any heavy object, the tension of a spring, the impulsion of a body to motion or the retardation of its motion, and other operations of this kind. On the other hand, the greater or less progress of a body once put in motion in a horizontal plane is not an effect of this kind from which I calculate absolute force. For the force remains the same during the progress of the body in this case. This is worth noting explicitly for the sake of avoiding error, since it has not been adequately explained. Of course, I admit that from a given time, or its reciprocal, the velocity, and from other known circumstances, a judgment is possible about the force of a given body. But I assert that not the time nor the velocity, but only the effect is an absolute measure of force. For when the force remains the same, the effect remains the same, and neither the time nor other circumstances can vary it. Hence, it is not surprising that the forces of two equal bodies are proportional not to their velocities, but to the causes or the effects of their velocity. In other words, to the heights producing them, or capable of being produced by them, or to the squares of their velocities. It also follows, therefore, that when two bodies collide, there is conserved after the collision not the same quantity of motion or impetus, but the same quantity of force. It follows also that a string must be stretched by a fourfold weight to produce a tone twice as high, for the weight represents the force, the sound, the velocity of the vibrations of the string. Did I read that? So it reads that. It follows also that a string, I find this fascinating that he has brought this in, must be stretched by a fourfold weight to produce a tone twice as high, for the weight represents the force, the sound, the velocity of the vibrations of the string. The ultimate reason, however, is that motion is not something absolute and real in itself. Wow, that is awesome. I never would have thought that.
I didn't know that we had to
Right.
stretch a string 4 times to get an octave higher. That's,
Isn't that
you have to put 4 times as much weight on a string to get 1 octave higher. That tells you how much power is in a piano.
There you go.
Holding all those
That's why it's a
strings.
machine, that's right.
That's why it's dangerous.
But I still don't understand why motion is not absolute. I don't quite get this notion about motion.
If we're reading it one sense,
Well, he's saying that the height to which a body rises is, how is the height of the body rises related to its velocity? If an object has twice the velocity, let's say body has twice the velocity as another one, how much higher can it rise?
Four times.
If it has twice the velocity, how much higher will it rise?
4 times.
4 times, okay. And conversely, if it falls, if you fall 4 times as far, you'll end up with twice the velocity.
That was our first
Okay.
example.
All right.
That was the first example.
Yeah. Yeah. So it's a little tricky. You have to, you really have to ponder this. It's not self-evident. One thing that occurs to me is that it's sort of Leibniz talks about the fitness of things, how things actually work out. So you can actually, the world works in such a way that you can actually equate force from being in motion with the force of falling. In other words, I think it has to do with, because you're dealing with each case, you're dealing with the mass is involved. In other words, the force acquired by a falling body is proportional to its mass, right? And the force of a moving body, say moving horizontally at a certain velocity, is proportional to its mass times the square of the velocity, but each case the mass. Now these are 2 different masses. One is inertial mass, and the other is, you could say, gravitational mass. And the thing, it works out. So it's not obvious why that should be. As Leibniz talks about, he calls it the fitness of things. And that's something really to ask yourself. I mean, you never hear this question. You don't hear this question raised, but I think it's, except Einstein discussed, right? Inertial mass versus gravitational mass.
He makes it, he proves that they're equivalent, certainly within his theory anyway.
Okay.
As compared to the fact that a lot of the critics would say that, no, Einstein is wrong. I mean, came up with some of these guys who wanted to say there's some difference. But certainly from Einstein's standpoint is, and this goes to what you were talking more about universal law, which also, for example, what Leibniz is dealing with is work, and he's saying that's more fundamental and more universal than what might appear to be differences caused by motion. For example, if you want to climb a mountain, it's the same amount of work, no matter what path you take.
Right, or how long it takes you.
Or how long it takes you to do
Stop
it.
and rest all night.
Oh, yeah.
Okay?
You could
The
go
total
this
amount
way.
of work that you're going to do is the same. It may be easier if you take 2 weeks because your muscles don't feel it the same way, but it's the same amount of work. So what's universal? Most people would think what's universal is the pain in your legs and how you feel, and therefore it's more work to do it one way than another. But it's not. And indeed, if you try to get something out of the descent, you're going to find that it's the equal. It's equal.
Just
One of the
as
things that
You mean
Einstein.
it's equal work coming
Yeah,
down?
yeah.
Yeah. So
For your
the
muscles.
you know, you might do it real quick and bang your head, but it's it's kind of funny if you think about it. But Einstein's view, this is what the reason that he called it relativity, which at one point he said he wished he hadn't, is precisely the opposite of what you think. when you hear the word at any rate. It's not relative in the sense that we talk about subjective or relative views.
What's the difference?
It's universal. He's saying that your physical principle has to be something that applies no matter who the observer is. So you're looking for a law that applies to all observers, whatever their velocity, whatever their motion. Therefore, motion is not real. It's not fundamental. It's not a universal characteristic, nor does it give you universal laws. Motion is relative, but universal principles apply to all observers. And in one sense, that's why it's never complete, because what happens if you find out there's some kind of activity that you hadn't taken into account? Now you have to take that into account to get a universal law.
Good question on that. In terms of the example of the mountain, I know when I went to West Virginia.
Speak up a little.
When I went to West Virginia, you learned there's two ways up the mountain. You go up the mountain, or you can go around the mountain and up.
Yeah.
One way, you're going 5 miles, and the other way, you're going 50 miles. So yeah, you're still taking the same weight up the same height, but there's also the difference between traveling 50 miles
But there
and
isn't.
traveling 5 miles.
It's not the difference. It's because you're gonna the amount of work to take the different inclines. And by doing it over 50 miles, you've changed the way in which you've had to do it.
Where's the difference? Because I mean, the difference between walking on a level ground 50 miles versus 5 miles. There's a big difference. Or is that what we're talking about in terms of the loss? Taking out the question of friction and other laws. That's where that comes
Because
up.
I mean, that's the diagram that we just went through. It wasn't kind of obvious, but that,
Scroll back to
that one seems to be this idea of trying to compare force of motion with these sort of dead after that.
That's what makes the point
After
that it
that.
doesn't matter how far you go on a flat plane. It's zero
Right.
energy, right? Zero force
Exactly.
on a flat plane, no matter how far.
No, keep going.
Ray says he needs to make that point.
No, you're going the wrong way. Go the other way. The other way. No, it's after the tube one.
Wait.
Oh, we
The
gotta
rest
go, right?
is just loss in terms of friction and like.
Keep going. Yeah, that one.
Yeah.
If C, I don't know what the hexagon is there for, but if C is in motion, the sphere,
Yeah.
that whatever force or energy or whatever it has from its motion will carry it up an inclined plane of any length to the same ultimate height,
Right.
assuming there's no resistance.
Yeah.
So that somehow that force of motion can be converted into raising it against gravity to a specific height. And that will be the same regardless of the path that it takes.
Yeah, he's doing this because people argued against him. They said it matters, the path matters, the amount of time involved.
That might be
That's
because
because
they would compare it to climbing a mountain or something,
Right.
where there are other
There
considerations
are other considerations.
that are.
Scroll down a second, 'cause I think that sentence that I just remembered was, I think a little further, just past it.
such an epic is descent.
It talks about the horizontal.
Right here.
It is worth noting explicitly for the sake of avoiding errors, this is not explained right. The greater or less progress the body once put in motion on a horizontal plane is not in fact this kind.
Put a bouncing ball in there.
So he concludes that this force is inherent in things, in matter. And from this, then allows him, then from this, he says, well, what regulates that? To what intention? That represents, he said, that serves an intention, that force. Okay? We're coming back to what you said about universal principle. There's an intention involved that we apply, okay? So the question is, what regulates that intention? And this is where he says you must have something like a mind. And he calls this, he said, this is this is something that's substantial. He said that which is active is substance. And substance by definition is active. That's something he had always believed. But then this gave him a handle on it for the first time. He had a specific way of defining the relationship of the substance to the otherwise passive matter. The thing that he actually emphasized, one thing that always bothered him was that the phenomenon of inertia. Why should it matter? You know, what keeps things from being set in motion when you bang them, you know, or what is it's a resistance to motion proportional to the mass of the thing. And he said that if he came up with all kinds of possible explanations, but finally he admitted we really don't know. And that fed into this idea of this, it's kind of a passive force. The force can be passive and resist being set in motion, or like or in an elastic collision, he's saying that when you have two things collide elastically, that basically the explanation is not percussive, but you're actually triggering the action of the force that's already there, the innate force. It's sort of like, you know, his idea about innate ideas, you know, that Plato also had in the Meno, the innate ideas that are set off by the right kind of education, you know, they're drawn out by process of education. So this is, in other words, it gave him a handle on the whole idea of the monad. Now, there's something equivalent to the soul in its own way in everything. We seemingly not alive. So this was the royal road to all his other things. It really hinged on that. Everything was ready, but he got that. Then he elaborated. It was from there. It took time, but then in about mid 1680s, he actually came to this thing in, I think, 1678. But it was in the mid 80s he basically went public with this whole new system of metaphysics. He basically reformed metaphysics. That's what he did. He created a whole new metaphysics, and this was the key to that, because it showed you that there was that associated with matter there has to be substance. And then even then people didn't understand it. They said, well, you know, the monad is something you can sort of, it's down to the smallest part. You can subdivide the monads. That's what Euler says when he attacks Leibniz. So you read the thing in his letters to a German princess attacking monads. But he completely misunderstood it. What Leibniz is saying is every bit of matter has a monad associated with it. Okay, that was the point of it. And matter in itself, he said, also, just like motion, he argued that matter is basically a phenomenon. Without the life in it through the monad, it's not fully real. So this it really brought it together for him. I think we should, you know, might be worth, you know, another session going through his stuff on elastic collisions, because it spells it out a lot clearer, and you need to see it and how the idea that he's telling you here, he actually applies it to collisions, and the idea of elasticity, and then with the elasticity goes the idea that of worlds within worlds. In other words, within the elastic body are parts that themselves are elastic, and with them are smaller that are also elastic. So you never end up with, quote, hard atoms. There are no hard atoms at the bottom. You have worlds within, you know. And this is the same, really the same method as in his calculus, where he talks about the infinitesimal not being, you know, it's still a thing, you know. It's still an entity. It's still a discrete entity. It's not a point. Were you talking about this last night at the meeting?
A little bit,
yeah.
not much.
So his work on the infinite, nature of the infinite and the infinitesimal is an essential ingredient of all of this work that he did, including his theology too, his notion of possible worlds. It's all goes together. So you see it as a system, and it's like Lynn, you know, with his ideas about, you know, about how the metaphor, the principle of the metaphor goes with physics. Any discovery is based on a metaphor, whether it involves, you know, social relations, society, or involves, you know, direct relation with nature. So see that Lynn really is today's Leibniz. Also, it occurs to me that if you read his biographies, like the Mackey book that Tony Chaikin reviewed, you see how Leibniz was considered, throughout the world. I mean, he went down to Italy, I think, in the 1680s on a project, and everybody wanted to talk to him. Everybody knew who he was. They wanted everybody. In the Vatican, in fact, they offered him to be the Vatican librarian, and he wouldn't take it because it meant becoming a Catholic. But anyway, the thing is that it's the way that Lynn is seen throughout the world. Okay, and you get a more idea of a sense of why it must be the case that Lynn is responsible for what we're seeing with the with the bricks and the transformation of the whole idea of sovereign nation states.
Is that what you mean when you said earlier that, since Leibniz, nobody has had a system of thought since?
I don't think so. You know of anybody, Phil?
Not in the same way, no.
That it's actually extended to every.
I mean, you have some
facet.
crazy stuff like Hegel and whatnot, but I mean, you could say he's got one system. He's got a night in which all cows are black, so to speak. But in terms of, Leibniz is rather a remarkable character. He did geology. He did work on medicine. He did work on, animals. In fact, I think some of the theodicy comes out of this kind of, the distinction between free will and final causes and efficient causes. He has a whole thing on animal bodies and it's hard to come on an area that he doesn't do important work on. History. He did the history of the Guelphs, and he did. The one project he had for his whole life was the history of the House of Brunswick, and the relationship to the House of Este, which is a Italian, and this is all to determine who had sovereign control over certain areas, and it was part of an approach that he had to, in effect, breaking up some of the empires and pulling something else together. So he did this his whole life. He never finished it, really. But, so he was a universal thinker of a remarkable breadth, you could say, and unity of thought. I mean, Lynn gives him credit for being sort of the first to express an outlook on physical economy, even though it's relatively small area of writing.
And the man that opened up for Lynn a knowledge of the universe as a whole.
Yeah.
When Lynn was very young.
Yeah.
Barely becoming an adult.
He's a character, that's for sure.
Well, let's go to the next universal thinker. Someone put on Steinberg's report. Second